Okay, so to apply these linear regression techniques into the outlier diagnostic, that is, how to find the outliers in our training data, especially when we assume the linear relationship between input and output y. Okay, so what we did is that we look at the final ends where we have this beta ls that we've learned from our system and use it with our testing. Notice that when we did this, like we multiply these two together, we actually done two things, like making two assumptions. First, we assume that beta ls is probably the best possible that we can get from learning. And second, we assume that that the relationship between x test and y test is exactly linear. This may sound redundant because when we solve for beta, we already have this linear assumption anyway. But anyway, this is like when we assume linear and when we apply it, when we use it, this is like a whole entire circle of what it looks like. But the thing is, when our data have outliers, right? If our training data have these outliers, it will reflect in the beta ls in two different ways, actually. The first way is that maybe you have a very wrong beta ls, or maybe whatever beta ls here does not really match or reflecting the properties that could help you map a test to the y test. Or maybe you can say it doesn't goes together, like it doesn't align with your testing. Okay, so in these two cases, it actually means one simple thing. It means that maybe you're training X versus X test. I mean, if you have a bad quality beta, if you have bad quality beta, that could mean that X that was training and X that is in testing are not representing one another. Or sometimes we may call it like a situation where our input when we deploy the model does not really, like, it's too challenging compared to our training data or whatever we get after training. So, or maybe sometimes we call this situation as our testing lies outside the distribution of training, or AKA out of distribution problem or OOD problem. But this is more like a words that people use in computer science, like out of distribution. Distribution. Yeah. Out of distribution problems. That's what we call when X test and X train are not really aligned. Then it will give you like a bad beta. Probably you would ask me then why I have to write to say that what if your beta ls is wrong. In this case where the beta ls is wrong, maybe something like the procedures that we've done to get the beta ls could be wrong. It could be like a pure miscalculation, or there are certain assumptions that you add into how you get beta ls is not correct. But in this case, when you only consider like the outliers removal, probably the only chance that you can get the wrong beta LS is when you compute linear regression. I mean, the compute the least square minimization, and you inaccurately compute something from this step. But yes, we will learn that actually there are methodologies to actually compute the new beta LS, but they will maybe using a different loss function, and that is when we call like a robust regression. That is the one that I said that they are belonging to the types of the robust method that kind of like making your machine learning more robust by sometimes changing the loss function, sometimes using whatever we call an estimator, or maybe change it to like a median estimator. Yeah. So that is pretty much it. Or maybe putting different weight to suppress the outliers. That's like the first step, like the first method in the robust regression. Yeah. So maybe in the simplest case, we will talk about like if we were to use just a normal simple linear regression, then we probably use like we will consider that the only problem with the beta LS is not really our calculation, but it is about a mismatch between X train and X test. So they do not represent one another, or maybe they have like the OOD problems, the out of distribution problems. Yep. And actually, to measure the mismatch, sometimes, especially when we are considering the case of linear regression, we can actually decompose beta LS into its like the formulation when it was like a linear, like a least square solution. And then we can see that actually, if you were just to consider between X test and X train here, then it can be written as a matrix hash. And this matrix, let's say if X test can well represent the training, or the training can represent the testing, then actually this should be about identical, like identity matrix. Because if you think about the dimension, let's say this is okay, X transpose here is like M times N. This one will be N times N. Therefore, sorry, N times, sorry, I'm N times M. And therefore, it will be like X test would be something like M prime, which is like a number of testing, times N. And then you have N times N as a dimension, and N times M. Okay, altogether you will have like a new matrix that is of size M prime times M, like that, or this H matrix. So it doesn't matter what your testing is, as long as they share the same feature dimension as your training, you can try to compute this relationship, or it is what we call the hat matrix. And after you have this hat matrix, you can use it to detect the outliers, or maybe the high leverage points among the input feature samples. So as I mentioned before, that at the end of the day, these inversions should somewhat be approximated by an identity matrix. This means that, well, for the edge that was around the off diagonal line, they should be somewhat close to zero. But the one that was at the middle here should be somewhat, like nearly identity matrix coefficients, which should be like a low value. And we will have like a proper value for these coefficients and a way to test. But to think about this, probably the one that is the outliers or leverage if it's going to be something that was wrong, it should somewhat deviating from the coefficients that was at the diagonal line as well. So to test this, usually they will compute the HJJ and compare that with the average of the entire coefficients at the diagonal lines. So that becomes these rules to detect the high leverage. So firstly, you may compute the H bar, that is like the average between the coefficients in the diagonal. And then it depends, like in this case, like a general one, they say that, if HJJ or the diagonal coefficients should have the value at about 1, then maybe this value should be less than or equal to the number of training samples divided by the number of testing. But to relax this boundary, because possibly there are other noises aside from the fact that maybe the training and testing doesn't mesh together. So sometimes they would put the threshold by multiplying with 2 to push the threshold up, so that if you find any HJJ that is outstandingly high, then you can say that that's definitely the leverage points. And to interpret the effect of the high leverage point, okay, let's say the high leverage point is probably the point HJJ that gives high value. But if we think about how this HJJ do when you multiply this H matrix back into this equation, because yes, the yellow one is the H matrix. If you multiply it with Y, if you have HJJ that is of high value and that's aligned with the coefficient of the measurements Y, definitely it should map you to some Y hat that is also of another high value. So this is like maybe like a graphical interpretation that whatever you get, if you have a high, this may not necessarily be X, it could be the HJJ here. It should give you like a mapping that's resulting the high Y hat here. But the thing is, aside from the fact that X could be like the input is wrong, your measurements, the reference could maybe containing outliers as well. So yes, even if you have like a low leverage point such as this point, but if the measurements aren't correct, right, you can still have like an inaccurate predictions or maybe the result from mapping anyway. But at least H matrix will help you like identify the input features samples that are definitely inaccurate. Yes, so that's all about the H matrix or hat matrix. Here's the example of how you may use it, and also one of your exercise will be checking this as well. And I would like to say that there's typo in it. Like this one's supposed to be 2m times m prime. Yes. And this as well should have same value. Yes. So the outliers are going to be those points that's above these lines. Yeah. And for this one, maybe some of that is like at the very edge. It depends on the characteristic of the value of this HJJ matrix. But in fact, we can decompose it. Like the factor that was inside this HJJ value, okay, which is as follow. Okay, let's go back to the H matrix that is computed this way. And in fact, another thing that I haven't said is that in this case so far, we talk about when we are using hat matrix with X that was like a testing samples, right? But well, we can apply it to the training as well. If we are suspecting that the proportion or maybe some proportions of our training data are not aligned with the majority of the data. For example, if you have the whole training sets that is, let's say, 1,000 samples, and maybe around 200 of it that you are suspecting that they may be outliers, then maybe you can put these 200 as your testing and that 1,000 for your training. And you can just maybe put them together like this and see if your y hat corresponding to these 200s are, aligned with your measurements. Or if you don't want to go as far as finding a test, you could just, multiply x together like that and see what is the hat matrix would look like. That's alternative. And also, another thing is that what if we just replace a test with x itself, right? Definitely, this should be something that look like a diagonal. We should have something that look like the identity matrix. But the thing is, what if it deviates from that? Then, of course, this technique can still be used to find a leverage within itself, that is HJJ, where you can decompose H into XJ transpose T and multiply that with the inverse of X transpose X inverse and multiply with XJ. This is another way to compute HJJ, but in this case, please denote that we are considering X to be all the training data that is from the same, like let's say there are xj within x, just like that. Maybe x, I'll put this way, x, which is a big one, contain maybe x1. Sorry, I'm not sure if I use 0 or 1. Okay, 1. Maybe containing x1, x2, and also xj, and up until xm, like that. You can also identify the outliers among your training this way as well. So that's what I was trying to say. Because if xj is really deviate from other x in general, it should become somewhat outstanding compared to the denominator that was x transpose x inverse. Yep. So that is like the way to look at it. And yes, everything about hat matrix is about looking at the input feature samples. Another situation is that after you have H matrix, as I mentioned before, you can compare it, the result of multiplying Y with H matrix, and see the deviation of that from the measurements Y. We can also try to identify the errors from the residual between measurements and the Y hat as well. But the problem with this is like we did not consider the scale of the Y. As I mentioned before, if you have Y minus Y hat, and if these values are in the scale of 1,000, it's very difficult to see if the residual of 1,200 is actually that bad. So that's the reason why when we want to extend our view beyond hat matrix to the residual, we probably need the methods to help us normalize of, give us a better way to judge the error with respect to the scale of the measurements at the training or maybe at the testing. But usually everything that we talked about here, especially from these slides, will be in the training. Okay. Because we are trying to monitor the outliers in our training samples, as we mentioned before. I think from here. Okay, I'm not sure if outlier in the training. That's the thing. Okay, so not there yet. Um, so in the next slides, we will talk about another two methods that one may use to remove the outliers. After we talked about the first one, that we can use this thresholding to remove the input feature samples. But the other two will be the methods to remove the measurements outliers. Nevertheless, there are slight difference between the hat matrix and these two. That is, um, when we test for the measurement outliers, and as I mentioned before, if we identify that, let's say, even for the input feature samples as an outliers, when we want to remove them, we not only remove that input samples, but we will also remove its corresponding measurements. Therefore, likewise, if we find that whatever samples that we have and the measurements are outliers, when we want to remove them, we will remove both the outliers in the measurements, the measurements with the outliers and its corresponding inputs feature. So we remove as a pair. And because eventually we remove them as a pairs, we can use the rest of the data to perform the regression again, or maybe to run the test again and see if we can remove the outliers. And then we maybe iterate the procedures again, that is, go back to detect for more outliers, remove them, and check the results. And that is like the procedures that we will see among these two methods. That is, okay, firstly, sorry, someone, okay, sorry. So firstly, we detecting the data point, that is outliers, measure the impacts, that is what's the difference between having that data sample and remove them. And then after that, we will decide whether or not they are outliers. So that's like procedures. It's kind of different from the head matrix. Head matrix, you have a threshold, that's it. Okay. Okay. For this one, because we will consider a situation where we remove the outliers, or maybe whatever we think that's outliers. Okay, the procedure will involve computing beta that was like the learned model parameters when we remove that data point. So in this lecture, we will denote it as the beta ls superscript j. And if you see the minus here, that means that we take that j sample out. For example, this beta superscript j, that is like a solution from our linear regression. It can be written as follow as we remove the j sample. Okay, we can compute it as like a x transpose x inverse, like that. So the denominator is still the same, but we remove the j sample from x and the j sample from y in our training. Therefore, we have like a new beta j's to calculate. And after that, we can use that beta ls where j is removed and test it with the egg test and see what we get from this as the prediction. After that, you may or may not notice the difference, but if you want to do this, then what you have to do next is that after you have y hat superscript minus j, that means this y hat came from the beta j that you removed, that j sample, or maybe this one here. Then you maybe compare with the scenarios where you haven't removed anything. So in this case, it's like the y hat, the normal y hat that came from x multiplied with beta ls. And please notice that when we say that we are removing the j sample in the training, it's actually only impact the beta ls that we get from the solution, like a least square solution, that is this um, equation, right? And we get the residual that is maybe denoted as the vector d superscript minus j. And in fact, let's say if our, okay, in this case, I kind of write it, the vect, the output, um, how should I say, the output prediction y hat here is like a vector. Okay, and probably you can guess that this vector, if it came from multiplying input x that was testing, and we have, let's say, m prime testing, then we should also have the m prime predictions as well. So that means that when we remove the j sample from our training, it will not impact the dimension of our testing, of course. But then we can use these facts to evaluate the the residual that is caused by removing the samples. And to do that, and of course, as we also mentioned before, that yes, actually with the previous method, we can do the same, where we have this like measurement minus the predictions, even though we would remove something out of h and y here. But the thing is, this error can still have problem with the scale. That is, for example, if our measurements is like in 1000, we have to again try to judge whether or not this error is high or low. And as a result of that, in this algorithm, they not only look at the residual, but they also try to standardize it, try to normalize it. So from these dj, it looks like a vector of samples. Sorry, the vector of residual samples. Okay. We normalize each of them with the RSE, the residual standard error. And for that, we can compute it using this formulation. So if you look at the residual standard error, actually, this is the one where you include the effect of when you want to consider that samples that you thought that it is a noise. Sorry. Or on the other words, this residual is including the reference, not reference, but it's like the prediction. Okay, I'll put this way. It include the predictions that came from noisy training data. Uh-huh. So that means it means that if DJ, sorry, actually DJ also already include the effect of having noisy and noiseless. So yes, both of them are the same. I'm sorry. Okay. Actually, both of them are the same. They're just normalizing. Sorry. Okay. Actually, with this, I'll put this way. If this value is high, that means that you have a very high effect of removing the J training data. And therefore, if the effect of removing J is high, I'm sorry. Okay. then that residual should be high, and therefore they should be removed. I'm sorry about this formulation. I was thinking of something else. Okay, is there any problem? Or is there any questions, any confusion?
No.
Okay, everything's so good?
Yeah, so far so good.
Yep, sorry. Okay, all right. Okay, let's move on. So that's the residual analysis. And yes, I'm not sure, but I think in our first lecture, let me share the screen a little bit. Or maybe I'll taught another one and then we can go over that because there are exercise and actually you can start doing it. So my goal will be for this lab is for you to implement the algorithm, maybe the H matrix. If I remember correctly, there are H matrix and the Cook distance as a function, and the rest of that, the codes already have everything for you. So that's like the task that you have to do in the lab session. I think I provide all the detailed information that maybe you can make the algorithm, but I think pretty much that's, yeah. So probably very much like if we finish this lecture, you can start doing the lab pretty right away. Okay, we will talk about it later, but let's finish this one first. Okay, and the last technique to remove the outliers is called Cook distance. And mm, for Cook distance is kind of similar to the residual analysis in a sense that it will consider the residual between before and after remove that that noise training samples from computing beta ls, and they want us to check the residual, like the core idea of these two techniques are the same, that is it still use this residual as the core in finding the outliers. But what is different between Cook distance and the residual analysis is the fact that in Cook distance they consider like maybe let's say it's like a least square, sorry, not least square, it's like a square error that also includes the effect. Okay, they consider the square error where they, I probably shouldn't say that they include the effects because both of them use y hat negate with the y hat superscript minus j, so they should be the same. But the thing that was different is that they further decompose y hat into like beta ls. And actually, Cook distance is, I mean, with this decomposition, it's just turned out that Cook distance is actually simpler to compute, but not with this formulation, of course. They actually have like reduced formulation, which is this one. And I have provided the derivation in page 31. Please don't worry about deriving this quantity yet, I think. Um, because, I mean, once you get this, the component within this equation, you can get the Cook distance right away. But maybe let's talk a little bit about why maybe computing it directly, and as well as for the residual analysis, why these steps aren't going to be easy. Okay, maybe with the residual analysis, we are seeing it right now. We understand what it's meant. So firstly, we maybe select the pair ij, we remove them, we measure the effects of removing, and we check whether or not that's beyond the threshold. And we will keep doing that for j every samples. Let's say if you have 1,000 samples, if you do it for every j, that means you have to loop this for 1,000 times, and each 1,000 times you have to compute this matrix, which is like I'm not sure. Like this may not be as bad because it depends on the feature dimension, but it could still be kind of bad if we have to multiply this 1000, like matrix of 1000 times something, and multiply with that inversion of something for 1000 times. But what if we have something bigger than that? It may not be 1000, but 10,000. So the one that will require most of the computation would be this step, and also these steps where you have to sum over m samples of your, yeah, it's just that summing of that m samples. So yeah, computing these aren't easy, in a sense. Therefore, and maybe I'm not sure what was the initial motivation for reshaping this residual analysis into the Cook distance. But one thing that we can see like towards the end is that Cook distance actually enable like a closed form formulation where you don't need to iterate like that. Okay. All right, let's start. Like how we came to this after we have this one. Sorry, this one. And actually, this one look very similar to the residual analysis, which is this one. Okay. Um, let's say if we believe, okay, this is J, I'm sorry, and J, I'm not sure if I use superscript J or subscript J. For Y, I am, oh, it's subscript, sorry. Okay. For J sample, I use subscript. Okay. Maybe I'll put this way. Sorry. Okay, so it's J sample is supposed to be like this. So let's say if this data pair is removed, so first thing you can compute like residual, right? This will be like a scalar because let's say if we have 1000 samples, we transpose it, so it become like one times 1000, and that is like 1000 times one. Nevertheless, um, even though okay it's like a scalar value, but we know that actually it came from the fact that we are computing the residual between y hat before removing and y hat after removing. And unlike the previous method where you consider only like y and y hat divided by that square error thing, the Cook distance would consider like would just consider the mean square error as the base of the computation because they want to normalize the square of the error. Okay, so that's it. Next thing that I've done, or maybe try to decompose from this initial formulation, is to further decompose beta hat into x times beta ls. Okay, but let's just look at the original formulation first, and let's see what's the meaning behind each of these components. So firstly, for some reason, which I've tried to find, I'm still not sure why, but they say that um, for the Cook distance, they will have this denominator n, which is the size of the feature dimensions. Probably their reasons could be something along the line of don't want the value to be like underestimating, which could means that, or maybe overestimating, which could mean that there's something about this MSE that may be allowing the value up here to be very high. Yeah. But anyway, the mean square error or just the error like it's like a generic error that we compute empirically when we have like two error vector And actually this error vector E, if I remember correctly, which I forget to write it here, E is simply y minus y hat, where y is the measurements and y hat is the prediction, and probably is the prediction including outliers. So okay, so that is like a square error between the measurements and the predictions with outliers. Definitely this value could be very high. But yeah, I'm not sure why they have to do this n again, but I'm guessing that if they do it this way, okay, because this could be very large, and if they do it this way, um, it's more like they're trying to use n to compensate with m minus n here. I'm not sure yet for the entire reason, but as I checked the formula, this is the correct formulation where they have n here, and that was m minus n, and this one is actually the prediction and the ground truth. Sorry, not ground truth, but the measurements. Yeah. Okay. Okay, let's go step by step. So that means that if you include some mean square error here, it's just like if your error is high, that means y hat will deviate a lot from your measurements. So this is a high value. But the question is like how far that was when you compare this distance with the one above. So it's kind of like that. And if it is like if our yj, I mean after we remove that outliers, somewhat turn out to be closer. Okay, I will just fix y hat there, and we say that what if our yj after we remove the outliers be something that is close to our measurements? That means that whatever the errors that we have here should be something that is as large as here. And therefore, dj will be about m minus n over n. Um, which means that actually in this case, they use 4 times, and it's just said that if it's larger or equal than 4 times minus n, which is possible if you use a lot of measurements, then we will say that j will be like the outlier samples. Yeah, because the value is high enough to negate with the mean square error. Question? Good. Okay. So yes, the gist is if y hat minus j is approximately close to our measurement, then what we have left is dj equal to 1 over n times 1 over m minus n over n. Okay, but what if it wasn't, right? I think that's more of the problems when it wasn't. Okay, what if yj, okay, so we have this as like our base thought where if we remove that j and it just make everything way better, then yes, this is dj, this dj high is probably bad one. Okay, another thing that is that what if y hat j is not equal to y. The question would be, then what this yj should have value as being. So the thing is, if yj wasn't close to y, very likely yj will be closer to the y hat superscript minus j. If it's not equal to y, very likely that means that when you remove that j sample, it does not make a lot of impact. So that means y hat j will be somewhat still approximately around y hat. So that means your dj will be around 0 or close to. So this means that is like the opposite case where you can decide that that is definitely not the outliers. But I guess that many of you will have this weird question or maybe some kind of weird thought. What if after I remove that j samples and I get a y, y hat j that is not equal to anyone, not equal to y or y hat? Is that possible? I'm guessing that is, I'll put this way. There are reasons as to why y hat superscript minus j in this situation has to be a value that is somewhat kind of like in between y and y hat. And the reason behind it is because of the linear assumption. If you have linear combination, it's like you can draw a line and they should somewhat continuously align together. Even though there are like this y measurements in your training that could be corrupted by your data, but somehow they should have somewhat like a linear continuous relationship between them. So you can think of it as like these two could be like the two opposite extreme cases of them. While I haven't yet came to the point where I derive this, but I think it is possible, especially if you look at this equation. Um, if you think about beta ls would look like that you have the beta j, sorry, I'll just make a better space. If you know that beta j is like this, right? Like you have n times n here, n times m here, but this one is like m minus 1, and this is like m minus 1 times 1, something like this. So pretty much if you write beta ls, just beta ls where you include everything, it would be like a linear combination. Like you having, I'm guessing, but I'm not sure, but maybe if one day I know it, I would let you know. It's like you are summing over beta j ls. I'm not sure, but we can discuss that later because I kind of forget already. It's, I think it's, I, okay, I think I kind of did it in a incorrect way. It should be beta j, just beta j, not minus j. What I mean is that this beta j will be x transpose x inverse x, and when we select only the j's row and yj, this could be the case. So it's like whatever we get as a beta j ls is like it's a linear combination of when we select only one component within it. So if we removed it, it's like eventually when you sum it up all together, it will become the y, y hat here that came from the beta ls there anyway. So this is like for me like a rough idea as to why you can use Cook assumption to detect, because somehow you can guess that result should be somewhere between just like the ideal case, the measurements where you have your ground truth, and may not go beyond that y hat. Yeah, is that okay? Okay. All right then. Let's move on. So actually, what we talked about is just like the first equation of how things came from. But the following lines here, maybe I wouldn't ask you to remember it because it's really very complicated. But anyway, you can try to derive it at home to see how comes I get from maybe this equation to something like that equation. And actually, I remember now, this equation will be the one that I would ask you to try to program or maybe implement on Python. Yes. And actually, how I came to this equation um, is something that could be derived according to this page 31. And the reason that we use this equation is because, as you can see, this dj would just corresponding to that j, where you don't need to iterate all over and try to do all the matrix vector computation that is very complicated. Like you can just compute everything just once. Like you can compute the H matrix once, and that's it. Like you don't need to keep recomputing everything, maybe 999 dimension multiplied with something again and again. Unlike that, the residual analysis method. And yeah, so it's more efficient to compute, and actually you can verify it by yourself, because I have the like the code for you. You can try different way, but I recommend that the easiest one is probably to program this line. Okay. Um, okay. Another good thing about this equation 5 is that it's actually written at the very bottom of the page. That is, another good thing about this is not just computation, but the fact is that the fact of why it's important is that um, you can see the impact that is happening due to the input features through the hat matrix, the H matrix, versus the impact that is causing this sample to be outliers through the residual. So it's kind of like helping you separate the impact between both sides. It's like for the one here will be something around how far your hat, sorry, your prediction y hat here is deviate from the measurements. Meanwhile, the second term will be something around how bad is the input samples. Just that. Okay. So that is all for this cook distance, and this is maybe an example. So we can use cook distance the same way as we use the residual analysis, where we have to set up a line, right? And then whatever beyond that line will be considered as outliers. So actually, it's simple to make this decision. If you can compute the cook distance. Yep. So another thing to notice about, as you can see, here they kind of plot the curves, not curves, it's like the dot between cook distance versus the samples index, which is like the index like j equal to 1, 2, 3 up until m, which are the indexes of your training data, stuff like that. So you can apply the same technique to your own work as well. Um, yep, pretty much. And last thing is about the robust estimation. Maybe before I start this one, I would like to take a little break because my battery is nearly run out again. And also, just a little recap about the. Actually, I put it on my course view already. You can. I'll just go through this. Okay. No. Okay. Log in. Okay. Okay. Just letting you know because I already let the other class know that now we have like a second lab and homework come out. But I guess it's not too bad because this one, it's not quiz. It's just like you have to implement it as a team. As you can see, they're all group based. So in here, this is like the notebook that you have to complete within time. I guess. I mean, if everyone can finish it, then yeah. But if no one can finish it, I will think about. But anyway, just like the same where you have group name and name of the person and collaborators. Then if you go scroll down, you will see that actually it's like whatever I would ask you to do here is to write the code for the hatch matrix, and you need to return the diagonal of the H matrix. You can try. It's not that difficult. It's like you can just plug in the formulation. Another thing that you have to do is the cook distance. Yep. And because we already have the H diagonal from previous function, then we can plug that in and use it to compute the cook distance. And with both, you can maybe do the performance comparison. For these, it's like I've already done it, so you can just use it. Or you can, if you want to plot or do anything further, feel free to do it. Actually, what I would grade, I mean, your score will be based on the accuracy of the cook distance and the hat matrix, and that's it. And actually, I thought that maybe I will see if it's possible. Like if all the students can finish this hat matrix and the cook distance, which maybe this would be like the lab, like the lab exercise. After that, the homework will be um, to point out, like to write this maybe lab report, like pointing out the difference between hat matrix and cook distance in the algorithm, and maybe discuss the results between them. And actually, I provide the Google Doc where you can copy it and use it as like a place. But yes, of course, at the end you have to export it into PDF file. But in this space, it's like you can type, analyze your results, discuss the results, and add a graph if you like. I mean, after after you've run your code, you get everything right, then you can use that result to report in here. Yep, because I think I prefer that you have like the space to show what you think. Yeah, I think that's all. Any question?
Sorry, Kacang.
Yes.
So we are allowed to start implement the coding for H matrix and code distance before the lab?
Yes, you are allowed.
Okay.
Yep, because I wasn't sure if that can be finished before. I mean, if I start there, then because I'm not sure if all students can do that, but I guess that if you do it right now, maybe if you have any questions, you can ask in the time where I start the lecture. Yeah.
And so for the first lab, we have the quiz, right? So the quiz will be our lab marks, is it?
Uh,
The
the
score?
quiz will be, yes, for your first session, first lab session. Yes.
So it's in a group or individually? Because like everyone did the quiz differently.
Um, Actually, I was going to get it as individual because I
I
cannot force that tool to collapse together. But I'll see. I mean, if you really prefer it to be like maybe group based score, it could be like average score if that's okay for you. I will see that because I haven't looked at the score yet. Initially, I thought I will look at it, but because right in the morning I have problems with my iPad, so I'm sorry.
understood.
Okay, any further question?
Um, so for next lab, which is next Monday, we just need to complete the task, which is the coding part. And for the question part is for the homework, right? We don't need to finish it on time, right?
Yes, that's
Okay.
right. Okay. All right, then let's take a break and we'll come back in next 15 minutes, which will be like 15, 23, maybe make it 25. Yes. So 15, 25. 3:25. Yeah. Okay. Okay. I'll